Hello everyone, welcome back. I am Divij. This is For the Love of Physics, and in today's video I want to solve the problem of a Dirac delta potential well scattering state solutions. So essentially the Dirac delta potential well has two different cases, one in which energy is less than 0 and we end up getting a bound state, and the other in which the energy is greater than 0 and the particle essentially has either a probability of reflection or transmission, which we will call as the scattering state solutions. Now I have made a video on the first case, a very detailed video on the first case. I will put up a link for that video somewhere in the description. If you are interested in the bound state wave function solution and the bound state energy eigenvalue, you can look at that particular video. It is a detailed solution for that case. In today's video, I want to look at the other case scenario, which are scattering state solutions for a particle with energy greater than 0. So, what is a Dirac delta potential? Well, it is a theoretical potential that is created by the Dirac delta function. I think most of you should be familiar with what a Dirac delta function is. It's a mathematical description or mathematical distribution that has this kind of a form to it. So it's 0 everywhere except for one point at which it is infinity. That's the Dirac delta, right? It might not be a very practical mathematical function, but it is a limit to a sequence of functions that has an increasing height and decreasing width. So for example, if you have a normal distribution, then you can create a limit of that particular normal distribution where the standard deviation is decreasing, the width is decreasing, height is increasing, such that the area under the curve is always equal to 1, then that would approach the limit of what we know as a Dirac delta function. So it's infinity at one particular location, x is equal to 0 and 0 everywhere else, such that if I integrate the Dirac delta function in the entire region, it comes out to be equal to 1. And if I multiply the Dirac delta function at with some mathematical function, so this here, the Dirac delta is defined at x is equal to a. So it's not necessary that the Dirac delta has to be located at x is equal to 0. This simply means that it's located at x is equal to a. I multiply that with some function, integrate in the entire region, I simply end up getting the value of that particular function. So the Dirac delta function has a lot of mathematical uses, and therefore in the context of quantum mechanical theory, we want to look at the standard solutions if a potential would look like a Dirac delta function. So here of course it's a inverted Dirac delta function because I am taking Vx is equal to negative of the Dirac delta potential at a particular value of x is equal to 0. Of course, alpha is some kind of a positive constant, and then we have the Schrodinger equation. So if I substitute the entire thing in the Schrodinger equation, then solving this Schrodinger equation gives us two different solutions, one in which energy is less than 0. So the particle is trapped at this particular position, x is equal to 0, the particle is trapped. It has a particular value of energy eigenvalue that I've obtained in the previous video. And of course, it has wave function solutions, which I've written here. I mean, you can just look at the previous video, or this is just for refreshing your memories. And of course, today's case, which is the scattering solutions where E is greater than 0. And that is what I want to study today. What happens if there is a particle which is approaching from the left, encounters this kind of an inverted Dirac delta potential well? Of course, the particle is not going to be trapped because it has energy greater than 0. So the particle is free to move around. But the particle will still interact with the potential, and as a result, the particle has a certain probability of either getting reflected back or a probability of transmitting through, which we can obtain by finding out the solutions of the Schrodinger equation. Again, if you're interested in the bound state solutions, look up my previous video. Today, let us look at the scattering state solution. So if I look at the Schrodinger equation for the scattering state solutions, I want to solve the Schrodinger equation first in the negative x-axis and in the positive x-axis, and that would help us figure out the solutions in a very simple manner. So I want to look at equation 1 in the region x less than 0 first, and I also want to look at the equation 1 in the region x greater than 0, right? And you would see that both the equations are essentially the same. So here you have minus h cross square upon 2m d2 psi upon dx2. What happens at x less than 0? The Dirac delta is 0 by definition. Therefore, I simply end up getting E psi. Same here, minus h cross square upon 2m d2 psi upon dx2. What happens at x greater than 0? The Dirac delta is 0. So this term vanishes by definition. So therefore, this is equal to E psi. Of course, E is the same because energy conservation, right? So this expression simply becomes d2 psi upon dx2 plus 2me upon h cross square psi is equal to 0. Same thing we have here, d2 psi upon dx2 plus 2me upon h cross square psi is equal to 0. The standard solution of these kinds of differential equations is quite common, and I think you must be familiar with also. So you end up getting oscillatory solutions, plane wave solutions for these cases. So psi x is equal to, I have a constant a, and I can write this as an oscillatory solution e to the power iota kx plus b e to the power minus iota kx, where k square is essentially nothing but 2me upon h cross square. Keep in mind that these are the solutions for E greater than 0, and because E is greater than 0, 2me upon h cross square is a positive constant. And similarly, for the positive x-axis, I will get a similar oscillatory solution, but I'm going to keep different constants because the constants need not be equal. C e to the power iota kx plus d e to the power minus iota kx. So these are oscillatory solutions, okay? These are oscillatory solutions, also known as plane wave solutions. So if you look at this particular diagram, essentially what we have is, we have a particle which is approaching from the left like this, okay? And there is a plane wave solution which is associated with that, and I'm going to call this as the incident wave, psi incident, okay? And this is nothing but a e to the power iota kx, because if you look at this expression, this is a forward moving plane wave solution, and b e to the power minus iota kx, this is nothing but the reflected plane wave. So once the particle is approaching from the left, it will interact with the potential, and it is also possible that the particle can get reflected back. So that solution is also possible. So this is the plane wave corresponding to the reflected wave. So b e to the power minus iota kx. Similarly, in the positive x-axis, here we have a wave that is moving forward, right? This is in the positive x-axis, which is c e to the power iota kx. Now, of course, what is this? This is the transmitted wave, the wave that has moved forward. It is associated with a particle that has gone to the positive x-axis. So psi is the transmitted wave. Now, if you look at the last expression, d e to the power minus iota kx, then I should have this kind of a wave which is moving in the backward direction in the positive x-axis. Now, if you look at this scenario, as I said, the particle is approaching from the left, going to the right, and the particle encounters this potential. So it makes physical sense that there is a plane wave solution moving in the forward direction. There might be a reflected wave solution moving in the backward direction in the negative x-axis. But in the positive x-axis, if the particle transmits through, there is a transmitted wave which is moving in the positive x-axis, but there is no possibility of a reflected wave in the positive x-axis, because for a reflected wave to exist in the positive x-axis, there has to be some reflection somewhere here, right? But theoretically speaking, the potential is zeroed up to infinity. So we have a case of a very ideal potential where a singular particle is approaching this kind of a potential jump or the potential drop. So there is no possibility of a reflection beyond x is greater than 0, right? So therefore, this possibility does not really exist. D is equal to 0. This possibility is not allowed because it doesn't really make sense. Why would there be a reflected wave at x greater than 0? There can be a reflected wave at x less than 0, but not greater than 0. So therefore, we have essentially these three plane wave solutions, right? An incident, reflected, and a transmitted plane wave solution. So now what do? Now what we can do is we can apply boundary conditions to obtain the values of these different constants. So if I apply boundary conditions, I can use it to obtain A, B, C, and therefore I can also use it to obtain the reflection and transmission probabilities. So at x is equal to 0, I want to write the wave function which is in the negative x-axis as psi minus and the wave function in the positive x-axis as psi plus. What do we get? So A e to the power 0 plus B e to the power 0. So essentially this is nothing but A plus B, and in the right hand side we have C e to the power 0, so it is equal to C. So A plus B is equal to C. Let's suppose this is point number 2. Okay. To do further calculations, I want to create space on the board. So if you want to take a snapshot, you can take a snapshot. You can pause the video here. I'm going to rub this portion of the board to create some space. So this is what happens when you have a chalkboard. You have to make sure that you rub everything properly. You're not able to, shift a certain area to some other place. That only happens in an interactive board, smart board these days. But if you use a chalkboard, then of course you have to be very careful with creating space. Anyways, if you notice, we looked at the Schrodinger equation in x is equal to 0 region and x less than 0 region and x greater than 0 region, but we avoided the point of x is equal to 0. Why? Because we are dealing with a Dirac delta potential, which is essentially an infinite potential, and we want the equation to make sense, because the moment we introduce an infinity in the equation, of course everything blows up and we cannot get any kind of a meaningful answer out of it. So we carefully avoided the infinite potential at x is equal to 0. But we want to work around that by, again, looking at the Schrodinger equation around x is equal to 0, but instead of looking at it at x is equal to 0, we will look at it in a region in which x is equal to 0 is present, and then we will take a limit where we tend towards x is equal to 0, and then we see how what results we get. So again, I'm going to look at the time independent Schrodinger equation that I have, but in this case I will look at the original Schrodinger equation, which is minus h cross square upon 2m, and then you have d2 psi upon dx2, and then you have minus alpha del x psi is essentially equal to E psi. So what I'm going to do is I'm going to look at this Schrodinger equation over a certain region around x is equal to 0. So I'm going to integrate this expression between two distinct regions. So one is, of course, at some x value minus epsilon in the left hand side, and another at an x value of plus epsilon. So between x is equal to minus epsilon and x is equal to plus epsilon, that is where I'm going to look at this particular equation. And of course I'm going to apply this integral across the board. X is equal to minus epsilon, x is equal to plus epsilon, integrate in the x-axis because energy is conserved, so it's a constant, so I can take it out of the integral, minus epsilon and plus epsilon, you integrate psi x with respect to dx. And then we're going to take a limit here, okay? I'm going to take a limit such that epsilon tends to 0. You see what I'm doing here? This is a technique that we can apply whenever we deal with Dirac delta potentials, because we cannot really solve the Schrodinger equation at the point where the potential is infinite. So instead what we do is we take a region around that point and then we make that region smaller and smaller so that there's a limit where this epsilon tends to 0. And let's see how we can simplify this. So of course, if you look at this particular expression, here we have limit epsilon tends to 0, and because this is an integration of d2 psi upon dx2, which is nothing but d upon dx of d psi upon dx. So essentially this is nothing but d psi upon dx, okay? And then you have the limits of minus epsilon and plus epsilon. Of course, you have the constants here, minus h cross square upon 2m. Let's keep note of that also. If you notice this expression, this is nothing but limit epsilon tends to 0 and alpha can be taken out. You have del x psi dx from minus epsilon to plus epsilon. And of course, what is this here? This is an integration of the wave function between minus infinity to plus infinity where epsilon tends to 0. Now keep in mind that the wave function is a plane wave solution. It's an oscillatory solution, but we have to have continuity even at x is equal to 0. So, which is what we applied here. There is a continuity between the incident plus reflected and the transmitted wave at x is equal to 0, which means what? It means that at x is equal to 0, the wave function has a finite value, right? So when I integrate the wave function around x is equal to 0, then I essentially end up getting the area under the curve, right? If you do integrate any kind of a mathematical function in a given region, you essentially get an area under the curve. So integration of psi x dx simply represents the area under the curve of psi x dx in that tiny region of minus epsilon to plus epsilon. So this psi x has a finite value. So integration of psi x should also be a finite value. But we are looking at the possibility of epsilon tending to 0. So if you can think of some kind of a wave function, right, at x is equal to 0 that has an oscillatory solution, and you look at the nature of the area under that particular curve such that the area has a breadth of minus epsilon to plus epsilon, then under the limit of epsilon tending to 0, we essentially get a rectangle with a finite length and a disappearing height, right? A finite length and an absolutely infinitesimally small breadth. So therefore, this limit tending epsilon tending to 0 makes this whole thing 0, right? I hope you understand, because it's a finite area with an infinitesimally small breadth. Under this limit, it becomes 0. So essentially, you end up getting 0 here. So therefore, I can rearrange everything and let me make it equal to 0 here. So this essentially becomes, so let me write the left hand side as del d psi upon dx, which is nothing but d psi upon dx at plus epsilon minus d psi upon dx at minus epsilon, and this is of course under the limit of epsilon tending to 0, which is basically equal to minus 2m alpha minus 2m alpha upon h cross square, and of course you have the limit again, epsilon tending to 0, integration of del psi x, right? So it's going to take some space here. So psi x del x dx, right? Again from minus epsilon to plus epsilon. Now here we can, I hope that this is clear to you. Everything is jumbled up, but if you are following the steps, it should be clear that now what we can do is we can use a property of Dirac delta function. So there's a property of Dirac delta function that if you have a Dirac delta function and you multiply that with a different function and you integrate in that region, we essentially end up getting the value of that function at the location where the Dirac delta exists. So it's kind of localizing the function at that particular point. So because we are taking the Dirac delta function, multiplying it with the wave function solution, but the Dirac delta function is essentially at x is equal to 0, right? So therefore, this ends up becoming, this entire integral ends up becoming nothing but the value of psi at x is equal to 0. That's it. This is at psi 0. So let us take this forward. But again, please forgive me for everything being so crammed up together. This is the best I can do because there are so many mathematical equations that I have to write them next to each other. Again, if you are following the steps, this is what we have. So now let me first figure out this expression, right? The left hand side. And to figure out the left hand side, I'm again going to use this space. Okay. So this space I've just kept because it's the header, right? Okay, this is the header. So what I want to do is I want to find a derivative of psi, but psi is this and this in two distinct regions, x less than 0 and x greater than 0. So if I have d psi upon dx, right, and I want to find it at plus epsilon, means I am trying to find this at x greater than 0, then essentially this is what I have. So this becomes equal to, what is that? That is iota k c e to the power iota k, but because x is equal to plus epsilon, this becomes plus epsilon, right? And again we have d psi upon dx at minus epsilon. So x less than 0, for that we have this solution, it becomes iota k, right? And a minus b, and then you have, okay, I should write this as a e to the power iota k, x is equal to minus epsilon and minus b to the power, b e to the power minus iota k, but x is equal to minus epsilon, so plus epsilon. But of course, this is under the limit, right? So if I apply the limit here, so if I apply the limit in both these scenarios, so here I will have, so this is equal to limit epsilon tending to 0, and this is equal to limit epsilon tending to 0. So this essentially ends up becoming, because epsilon is 0, this is iota k c, and this is equal to iota k a minus b, right? Now, so using these two here and then writing everything here, okay? Let me write the whole thing here. So what is this? This is del d psi upon dx, which is equal to this minus this. So d psi upon dx at plus epsilon is equal to iota k c, and minus d psi upon dx at minus epsilon is iota k, I can take this as common, c minus a plus b, right? And this is equal to the value of the wave function at x is equal to 0. That's it. I have a new kind of a boundary condition now. Of course, there is the constant minus 2m alpha upon h cross square. So essentially I end up getting this boundary condition that iota k c minus a plus b is equal to minus 2m alpha upon h cross square psi at 0. So this is going to help us further obtain the values of the constants. So let's take this calculation forward. Okay. So what we have here, iota k c minus a plus b is equal to minus 2m alpha upon h cross c h cross square times psi 0. For psi 0 I can take this, right? This is also a valid solution. So if I put x is equal to 0, then I essentially end up getting a plus b. Let's simplify this whole thing, but before that let me take the constants to one side, okay, or iota to one side. So you have c minus a plus b is equal to, if I take iota this side, the minus will get cancelled and I will end up with 2m alpha iota upon k h cross square a plus b. Okay. So on one hand we have c, and on the other hand we have a 1 plus 2m alpha iota upon k h cross square a, right, 1 plus this, and we have for b this minus 1, I should say minus 1 minus, you have 2m alpha iota upon k h cross square b. There you have it. So let's suppose this is point number you have 3b. Okay. So now we have from one boundary condition a plus b equals c, from the other boundary condition this plus this is equal to c. So I can make both of them equal to further get a ratio that I am interested in. But before we move forward, I need to clear some space. Please take a screenshot of this video if you want. Note this down or pause this video. I'm going to create some space. So we have obtained in point number 2 that c is equal to a plus b, and in point number 3b that c is equal to 1 plus, I'm going to write all of this constant as beta, okay. So 2 iota beta a minus 1 minus 2 iota beta b, where beta is equal to m alpha upon k h cross square. So beta is equal to m alpha upon k h cross square. So that way this is 1 plus 2 iota b minus 1 minus 2 iota b. So now of course you know what to do. I can make both of them equal, right? So this becomes a plus b is equal to 1 plus 2 iota beta a minus 1 minus 2 iota beta b. So from here you can clearly see that on one hand the a gets cancelled, right? So here you have a, and here of course you have a. So this also gets cancelled, and that way we can obtain the ratio of a and b. So if I take b to this side, so this essentially becomes 2 iota beta a is equal to this plus this. So 1 plus 1 minus 2 iota beta b. So this becomes 2 minus 2. So this is essentially nothing but 2 iota beta a is equal to 2 1 minus iota beta b, right? So now we are in a comfortable position of figuring out a ratio of b upon a. So if I find a ratio of b upon a, this is nothing but iota beta upon 1 minus iota beta. Now why is this ratio of b upon a important? Because this will give us an idea about the reflection probability, b upon a, the reflected wave upon the incident wave. Okay. So if I have b upon a, which is this, then the reflection probability is quite simple, right? So if I am interested in finding the reflection probability, that what is the probability that the particle encountering this kind of a Dirac delta potential will go back, that is nothing but R is equal to B upon A mod square. So this is essentially the amplitude mod square of the reflected wave upon the incident wave. So what is this? So this is iota beta upon 1 minus iota beta times minus iota beta upon 1 plus iota beta, right? So iota and iota becomes minus 1, minus minus gets cancelled, so you end up getting beta square. And here you have 1 minus iota beta and 1 plus iota beta, this becomes 1 plus beta square. So this is equal to nothing but 1 upon 1 plus 1 upon beta square. So we have obtained the reflection probability. So if I substitute our expression here for beta, then I end up getting the reflection probability is essentially just equal to 1 upon 1 plus, so beta square is m square alpha square in the denominator and k square h cross to the power 4. Now we know what k square is, right? If you remember, I introduced k when I was talking about the Schrodinger equation here. So 2me upon h cross square. So k square is equal to, you have 4m square e square upon h cross to the power, no sorry, k square is just equal to 2me, sorry. So this should be 2m e upon h cross square. So this should therefore become, so what are we looking at here? So let's just simplify this in this region, okay. So what is 1 plus beta square? So beta square, okay, so let's write it down here. So beta square is equal to m square alpha square upon k square, but k square is equal to 2me upon h cross square, and then you have h cross square, right? So therefore h cross square gets cancelled, m gets cancelled, and this is nothing but, beta square is nothing but, you have m alpha square upon 2e, is that correct? M alpha square upon 2e. I think that there is something missing. Yeah. M square alpha square, and this should be h square, h cross square, and again another h cross square, right? So I'm missing an h cross square. So this should be e h cross square. So beta square is equal to m alpha square upon 2 h cross square e. So therefore this becomes, this is 1 upon beta square, so this is 2 h cross square e upon m alpha square. So m is the mass of the particle, e is the energy of the particle, h cross is Planck constant upon 2 pi, and alpha is of course the scaling constant that we associated with the potential initially, right? Alright, so this is the reflection coefficient, and because reflection plus transmission is always equal to 1, I can always do 1 minus r to get the transmission coefficient, or I can also get transmission coefficient from a different method. How? Let me show you. So this is the reflection coefficient here. So transmission coefficient can be obtained from equation number 3. So equation number 3 says a plus b is equal to c. So for transmission coefficient I need c upon a. So this becomes c upon a is equal to 1 plus b upon a. But what is b upon a? B upon a is equal to this. So this is 1 plus iota beta upon 1 minus iota beta. So this becomes 1 minus iota beta plus iota beta. So this becomes 1 upon 1 minus iota beta. So finally we also have the transmission probability c upon a mod square, but let me first find out c upon a. So this is nothing but 1 upon 1 minus iota beta, right? And if I do a mod square, then this essentially becomes this times 1 upon 1 plus iota beta, which is nothing but 1 upon 1 plus beta square. Therefore, this becomes the transmission probability is equal to 1 plus 1 upon 1 plus beta square is m alpha square upon 2e h cross square. There you have it. This is the transmission probability. So essentially, whenever a particle is encountering a Dirac delta potential, you end up getting situations where you have oscillatory solutions or plane wave solutions for the particle which is incident, that is also likely to get reflected or transmitted, and the probability of reflection is this and the probability of transmission is this. Now, I know that this is a theoretical problem because Dirac delta function are not real functions as such. I mean, you can't have a realistic potential like this, but these are all ideal mathematical potentials that are of great interest in the study of quantum mechanics, and hence I have derived it for you. If you wanted to know about it, then I hope that you have understood what's happening. I want to show you how the reflection and the transmission coefficient actually looks like. If I plot this whole thing in a graph, all right, if I plot these expressions in a graph, this is how it should look like with respect to energy, because h cross m alpha, these are all constants, right? So if I look at the reflection and the transmission coefficient, or the reflection and the transmission probability with increasing energy, this is how it looks like. One thing is kind of clear from here, that if the energy is very, very low, so of course the energy is greater than 0 by definition, but if it's a very small number, then the reflection coefficient or the reflection probability, sorry, dominates. That means a particle will most definitely be reflected back. So even though we are dealing with a delta potential well, and the particle has a greater than 0 energy, even then the particle, the moment it interacts with the potential, is more than likely to get reflected back. But if we look at a really large value of energy, then the particle is most likely going to go through. The transmission probability becomes approximately equal to 1. So for low energies, particle will most definitely get reflected. For high energies, particle will most definitely transmit through without being affected by the potential at all, which is kind of interesting. And you can include this kind of a graph in your paper if you are asked for this kind of a derivation. So yes, that is all. You can take a snapshot of this particular frame, pause the video, or you can draw this graph. We have solved in today's video, as well as in our previous video, the detailed standard solution of a Dirac delta potential for both bound state solutions and scattering state solutions. I hope you learned something from this video. I will see you with a different topic in the next video. I am 𝑓𝑬𝏬𝏬𝏬𝏬𝏬. This is For the Love of Physics. Thank you so much. Take care. Bye-bye.